here, what I need to do is I need to study f of z. So let's suppose, we'll suppose that f of z1 converges. In other words, you know, z1 is an element of the disk well, let me just, f of z converges. Let me not burden you with more jibber jabber. Where, and we're going to put f of z simply equal to the sum n equals 0 to infinity of like a sub n z to the n, okay? Man, all my black markers are dead. So sad. Maybe there's one up here that's working. Kind of, sort of. Ah, rats. Okay, so the thing is, if we can prove it at 0, if we can prove it for this one, the one that's centered at 0, we can transfer the result to other points through a simple lemma, okay? And we'll talk about next time. But so I would like to prove that this function is necessarily differentiable at the point where it converges. So the theorem of Carathéodory, what I want to look at is I want to look at f of z. Let me leave my, I guess I got enough room here. F of z, famous last words, minus f of z1. So what are we up against here? We've got the sum, n equals 0 to infinity of a n z to the n minus the sum, n equals 0 to infinity of a n z1 to the n. Now, admittedly, I'm getting, you know, I'm going to have to use things we'll probably prove next time. You'll forgive me, right? So, or maybe I just won't prove them next time because they're boring. Like, hey, that sounds better. But what happens here when you subtract these two? Notice that they both start with a sub 0. See, z to a power 0 is defined to be 1. So the constant terms cancel. And we're just left with the sum n equals 1 to infinity, you see, of a sub n times z to the power n minus z1 to the power n. All right? So far, so good? You guys like factoring, right? So we can factor out a sub n, and then what we got here is z to the n minus 1 plus z to the n minus 2 times z1 plus plus z1 to the n minus 2 plus z1 to the n minus 1, close a parentheses, times z minus z1. Obviously. No, I'm actually not joking. Like, this is a pretty standard, you've probably done this in abstract algebra at some point. It comes up if you study the cyclotomic polynomials. For example, this calculation's there. Playing with the roots of unity, this ends up coming up there. Do you see what I did? Does that make sense? Multiply it out if you don't believe me. If you multiply this out, you get z to the n, and you get a sum of a bunch of things. Then when you multiply by minus z1, you get this z1 to the n with a minus, and then minus a bunch of things. But the things are the same, and they cancel. So what does this all mean? This means that if you tilt your head and squint, you can do like a so, because what's outside of the parentheses does not depend on n. So you're looking at a series multiplied by a constant complex number. One of the properties of series that we can prove is that if you've got the sum of a sub n times c, you can pull the c out of the sum at such points where the series converges. Now, there is a question, the non-trivial question, as to whether or not the series that I've written in the red, this is actually a convergent series. There's something to be concerned about there, because we're adding up a bunch of things and the number n is going to infinity. It's concerning that that might diverge. It doesn't, though. But we don't have the technology to prove that yet. But listen, that's the pattern we want, right? So the theorem of Carthy-Adoree says look at f of z minus f of z1. That should be equal to the Carthy-Adoree function at z times z minus z1. So this in red is our candidate for phi of z. We need to prove, if we're going to prove this, we need to prove that that's actually continuous. So if we calculate the limit as z goes to z1 of phi of z, what does that amount to? Well, let me write out more carefully what this actually means. We're looking at the limit as z goes to z1. And how do you make this series careful? Like, what's the precise definition of that? Anytime you have a limit going to infinity in the series, that actually is impliciting another limit, a limit of the sequence of partial sums. So if I introduce k goes to infinity, that's actually the sum. K equals 1 to n. No, my bad. N equals 1 to k. My bad. N equals 1 to k, right? And then you've got your a sub n z to the n minus 1 plus z to the n minus 2 times z1 plus plus z1 to the n minus 2 plus z1 to the n minus 1, right? So I'm just going to focus on the Carthy-Adoree function, yeah? So look here, if I can switch the order of the limits, if I can flip those limits around, if I can bring the limit over z1 inside, what happens? What happens when the limit as z goes to z1 hits this for finite k? Think about that. Tell me what happens.
The stuff inside the parentheses collapses to n times z sub 1 to the n minus 1.
Ah, the stuff inside the parentheses collapses. So what are you using? You're using what? You're using limit laws, right? Which we can do because what I'm writing in red right now is in fact the limit of a polynomial, albeit an ugly one. No, what am I saying? This is a beautiful polynomial. It's beautiful. 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 So this here is a polynomial in z, and we've proved limit laws. I typed notes on limit laws. Some of you read them. It counts, right? So we have limit laws, which means we can evaluate a polynomial. Polynomials are continuous, which means we can just plug in z1. And as Ben has pointed out, there are exactly n-fold terms. And every last one of those in the limit z goes to z1 becomes z1 to the power n minus 1. So what you're looking at is the limit as k goes to infinity of the sum n equals 1 to k of a sub n times n z 1 to the power n minus 1. Now, the theorem of Carthy-Adoree says what? It says that the limit of the, if this function is continuous, and I would argue that it is because of this calculation, then f is differentiable at the point, and the derivative is the limit of the Carthy-Adoree function. So what this calculation all means is the derivative with respect to z of the power series n equals 0 to infinity of a sub n z to the power n is, guess what? It's this power series, n equals 0 to infinity, of n, a sub n, z to the n minus 1. And of course, we can erase that 0 and put it with a 1, right? So this, up to a little bit more writing, proves that the derivative of the power series is the term-by-term derivative of the series. Yes, Ben. Other Ben.
How did you get from, how did you change the index in that second step? You had gone from n equals 0 to infinity to...
Oh, this is the definition. N equals, oh, for one thing, thank you. Typo, 0, 0. That's probably not what you're asking about. This
Well,
by...
that was actually initially.
Oh, okay, but this by definition is the limit of the sequence of partial sums, which is what we're looking at.
And that would start at n equals 1?
Ah! Same typo. Thank you. Thank you. Rats, what happened?
But it's still valid if n equals 1, right?
Oh! Ah! Untypoing, untypoing. Sorry, I'm sometimes gullible. Yeah, that was 1 because, as I said at the start, n equals 0. This is just a sub 0 minus a sub 0, which is 1. So like, just drop that because it's in the way.
Okay. And it's okay that you drop that because in the limit, that 1 won't matter?
No, it's just identically gone. It's just algebra. It's just not there. It's not a limiting argument. That's just not, like when I take the difference of two power series with the same constant term, the constant terms cancel.
Oh, then it's equal to 0, not 1.
Right. And then yeah.
0, 1. A naught minus a naught would be 0 naught.
Oh, did I write 1? Oh, good grief. What's wrong with me? Well, many things, but there's one of them.
Okay, that makes sense, yeah.
So this is very exciting because this means that any power series is holomorphic on its domain because it has a derivative. And not just that, the derivative we can calculate like polynomials, right? What's the derivative of hyperbolic tangent of z? I don't know. I'd have to work it out. What's the derivative of a power series in z? It's term by term, I do it, right? Now that we have this, we can give the actually more proper definitions for all of our elementary functions. Like we can define sine, cosine, the exponential. All of these guys have definitions in terms of power series of complex numbers. Once we finish, a few more theoretical niceties. I'm still working on the notes for this, obviously, right? But the thing I sent you guys a link to, it's a pretty good book. I almost used it. I think Fisher has more good homework problems in it. Let's see here. What else was I going to tell you? Well, any questions while I'm thinking of my question? Yep.
You said you wanted to pass back on.
Oh, excellent. Excellent question. Let me do that. Anyway, that's where we're going next time. We'll work out properties of the power series and see what it gets us.